right? And if we look at our shear on element B, right? With the Vx is 16 times 10 to the power 3, okay, Q is equal to 0 tau. So for the 16 times 10 to the power 3, which is due to the Vx, our shearing stress is due to equal to 0. Because at point B, it is at its terminal, okay? So now if we look at point B due to Vy, means Vy is coming in this direction, right? It's inducing a shear, right, of 19.232. So now if we're going to draw the element now, for element B, the element looks like this. And we know that the shearing stress is doing this, right? And the value that we calculated is good 19.232. Okay. So with this, we again need to find out the normal stress at point B, right? Or small b. And this will be equal to, again, we know it's minus pz over a. We know we have my over iyy multiplied by x. And we have mx over ixx multiplied by y, right? So if we look at moment about y, okay, which is this moment we have over here, moment about y, we know that it's going to go under tensile. Okay, so moment about y is positive. And if we look at about moment about x, okay, moment about x is exactly as its neutral axis, so this will be equal to what? 0. Why this is equal to 0? Okay, so this term over here, this entire term is equal to 0. This is because y is equal to what? 0. Okay, so if we look at the y, so this is the y direction, is exactly what? It's exactly at the center, right? Based on the shear stress, based on the normal stress distribution, right? So from here, we only need to care about pz over a plus by my over iyy multiplied by x. We no need to care about this term because it's equal to 0. So this is equal to minus 100 times 10 to the power 3. Divide by a, again, is the same, 5310 times 10 to the power minus 6. Now we have plus moment about y is 9600. Divide by 40.9. No, divide by 9.061 or 9.01 times 10 to the power minus 6 and x. Okay, because it's exactly on the element is on the surface over here, x. So our x distance is basically equal to our thickness of the web. So thickness of the web is 0.072 or 7.2 times 10 to the power minus 3, and we just halve it. Okay. So some might say it is equal to 0, but it's not. It's 7.2 times 10 to the power minus 3. So this will be equal to, so this part is still the same, minus 18.832 times 10 to the power 6 plus 9600 multiplied 7.2 power minus 3 divided by 2. divided by 9.01 by minus 6 is equal to 3.836 times 10 to the power 6. Let me do it again. Yep, it is. So this answer will be equal to 18.832 minus by 3.836 is equal to minus 14.996 times 10 to the power 6 Pascal. Okay. So we know that this has a normal stress in compression, which is equal to minus 14.996 times 10 to the power 6. Okay. So now we have the elements and the associated stresses. Okay. So the next thing is, where are we going to go from here? Right. So if we were to recap the note on Tuesday, if we look at this table, right, and we focus on the yield strength, right, we focus on the yield strength, right, and we focus on the normal stresses, we know that all these value over here, the yield strength is over here, right, all these value, these are all the what? Principal stresses. And this data, right, if you were to recap, it's all carried out in what? Uniaxial direction. So it can be either be tension, it can either be in compression, or it can be either be shear, right? But if we look at our structure, right, it's under combined loading. Okay? Let me reverse a while. When they do a test, right, the elements look like this. So what you see is there's only a what? A normal stress. Okay, right? So let me copy this. And let me copy this. And let me do, right? So this is from uniaxial. Tensile test. And if you look at our structure, I'm going to pick element B. Right. If we look at our structure, and if I were to draw a transformation, it is not the same. I.e., right, you have stress Y or stress Z, which is equal to minus 14.996 times 10 to the power 6 Pascal. And you have a shear. And this shear, so this is shear ZY, which is equal to shear YZ, and this will be equal to 19.232 times 10 to the power 6 Pascal, right? So if you look at the uniaxial tensile test, okay, the data that we get, which is this data, right, which is this data over here, right? These were quiet, right? All these are the principal stress. Okay. So at the end of the day, right, we want to use the data from the table to calculate, for example, factor of safety, which is equal to stress uh, stress yield, for example, divided by stress allowable, right? The yield that we get is by what? Uni-axial. For now, the stress allowable is non what? Uni-axial, right? It has a combination of normal stress and shearing stress. Okay. So next thing we have to do is to use or to analyze element A or element B to determine the principal stresses using 3D Mohs circle. Okay, which is what I'm going to introduce to you now. Okay, I'm going to draw 3D Mohs circle, but not to worry. For today, I will teach you 2D Mohs circle first. So this is like the introduction to the next chapter. Okay, we will construct. I'm going to just introduce you what 3D Mohs circle look like. Then I'm going to start with 2D Mohs circle, moving to 3D. 3D Mohs circle is only 5% more difficult than 2D Mohs circle. Okay, so it's not something that is totally new or impossible. You have to construct 2D Mohs circle first, then to go to 3D, it's just a little bit more information you need to know. But I'm going to construct 3D Mohs circle because we have an element over here and the element is in 3D. Okay, so how does this work? Right. So I'm going to, as I said, I'm going to construct 3D Mohs circle. Now this might look strange to some of you, and it's normal because you have not done Mohs circle yet. Okay, so I'm going to just introduce it to you. Right. We have an element over here. Right. So if you look at our stresses, we know that our stress X is equal to 0. Okay, so if you ask me, Eugene, where is normal stress X? This is normal stress X, right? And it's equal to 0. Then you have stress Y, which is also equal to 0. And then you have stress Z, which is equal to minus 14.996 times 10 to the power 6 Pascal. Okay. And then we have our shear in the ZY, is equal to shear in YZ. This one we calculated is 19.232 times 10 to the power 6 Pascal. And under this configuration, don't worry about this, later I'll teach you, is what we call positive shear. Okay. Then the rest of the stresses, shear in the XY is equal to shear in the YX is equal to 0. So some of you might ask me, Eugene, where is shear in the YX? So this is shear. I'm going to change my color now. Okay. So this is shear. I have to be shear. So this one I've just drawn in red. This is shear. So the intersecting plane is Y and it's going X. Okay. And this is equal to shear XY is equal to 0. And then the last one, shear in the XZ is equal to shear in the ZX, and these are equal to 0. Okay. So you might ask me, Eugene, where is that? So shear, the intersecting plane is okay. So the last one, I'm going to change color again. Okay, so this is shear. The intersecting plane is X and it's going with Z, and this is shear ZX. Okay, so there you go. So now we know all our